Alright, logic lesson 6, logical proofs and arrow out rule. So today, finally, we are going to learn a method for proving arguments valid, and we are going to prove an argument valid. But first, as always, a little review. Arguments are composed of statements. Some of those statements are premises. Both basic premises and intermediate conclusions are premises. And of course, the conclusion. Arguments are composed of statements, premises, conclusion, and inferences. And this is the concept that's going to be important in today's lesson. Inferences are the logical steps that move from premises to conclusions. Simple arguments have one inference. You move directly from basic premises to final conclusion. Most arguments are complex arguments. They have more than one inference, which means they have intermediate conclusions between the basic premises and the final conclusion. Inferences, the logical steps moving from premises to conclusion. We remember that sound arguments have all true premises and are valid. We know that only statements are true or false. Only reasoning, inferences, and arguments are valid or invalid. For today's lesson, keep in mind that inferences and arguments are valid or invalid. It's the logic that makes them valid or invalid. When we want to know if an inference or an argument is valid, we need a precise definition of validity. You should really have a grasp on this one by now. You should be able to say it by yourself. An argument is valid when, if all the premises were true, it would be impossible for the conclusion to be false. Validity has to do with the logical connection between the premises and the conclusion. The connection, the way that they're connected, is what we're looking for when we're thinking about validity. The form of the argument, not its content, is the best way of establishing that there is or is not a logical connection between the premises and the conclusion. The form rather than the content of the argument shows the logical connection or lack thereof between premises and conclusion. So to capture the form of an argument, we learned in the last lesson, we symbolize all the statements in the argument. We symbolize to capture the form. Once we capture the form, we can see the logical connection, and seeing whether that logical connection is there is how we know if it's valid. So, once we have symbolized the argument, we demonstrate that the argument is valid by proving that there is a logical connection between premises and conclusion. That's what we're going to learn about today, is proving the logical connection between the premises and the conclusion. So this is the new stuff. We prove the logical connection between premises and conclusion by showing that each inference from premise to intermediate conclusion to final conclusion is a valid inference. If every inference in the argument, if every logical step is a valid logical step, then the whole argument is valid. And that's what proofs do. Proofs show that every step you can get from premises to conclusion using valid inferences at every step. So, in order to prove that we can get from premises to conclusions using valid inferences at every step, we're going to learn some inference rules. Inference rules are valid patterns of inference based on the form of the statements. The form of the premises and the conclusion are logically connected in such a way that if the premise were true, the conclusion of the inference would necessarily be true. Okay, so let me say that in a different way. An inference rule is a pattern of inference, a pattern of making a logical move from premises to a conclusion that guarantees that that connection is a logical connection, a connection where the premises imply the conclusion. It's a pattern. An inference rule is a pattern of inference which guarantees the logical connection between the premises of the inference and the conclusion of the inference. If we can use a valid inference rule at each step to show that we can get from premise to conclusion. Let me say that again. If we can show that we can get from premises, basic premises, to final conclusion using a valid inference rule or a valid pattern of inference at each step, then we show that the argument is valid. Okay, so let me say something about inference rules, because you might be thinking, like, how do I know that the inference rule is valid? What guarantees the validity of the inference rule? We can divide inference rules or patterns or forms of inference into two different kinds. We have basic valid inference rules and derived inference rules. Basic inference rules are patterns of inference which we can't prove validity using other more basic patterns of inference. Basic valid inference rules are patterns of inference which cannot be proven valid using other inference rules. Instead, the validity of these most basic patterns of inference has to be self-evident. It has to be self-evidently valid. And in fact, most basic valid inference rules are so self-evidently valid, the logical connection between premise and conclusion is so self-evident that you might find yourself thinking that they're silly or obvious. You want to skip them because they're so valid. Don't skip them. There are other kinds of inference rules, derived inference rules, or patterns of inference which are valid, but which we can prove they are valid using the more basic inference rules. Okay, so basic inference rules are ones that are just self-evidently valid patterns of inference. Derived inference rules are also valid patterns of inference, but we can prove their validity using the basic valid inference rules. And the reason I'm sticking on this point for a little while is because in this class I want you to stick to the basic rules. You're going to be tempted, you're going to want to use some of these derived rules. I call them shortcut rules here, and I'm not going to let you until you're able to prove that those shortcut rules are valid using the basic rules. So in this class, we're going to mainly be using these basic rules. There are going to be 10 basic rules that I teach you, two for each of the 5 logical connectors. Right, so we have if then, conditional, and, or, if and only if, and not. Each of those logical connectors has 2 basic inference rules associated with it. Okay. If we demonstrate that we can move from basic premises to final conclusion using only valid inference rules, then we prove that each inference is valid and therefore that the argument itself as a whole is valid. So that's what the method of proofs does. The method of proofs is a way of showing that we can get from the basic premises to the final conclusion using only valid inferences at each step. I'm going to show you this method of proofs in just a few minutes, but first we need a valid inference rule to be able to do a proof at all. So here's our first basic valid inference rule. arrow out rule. So you can guess that this rule is associated with the if-then, with the conditional logical connector. The arrow out rule says from two premises, one of which is a conditional, and the other of which is a statement or formula that matches the antecedent of the conditional, you can infer the consequent of the conditional. So learn this rule. Don't just memorize it. Understand it. See for yourself why it must be valid, and a few things to notice about it. To apply this rule, you'll always have to have two and only two premises, one of which has to be a conditional, and the other has to be the exact match of the antecedent of the conditional. It has to be an exact match. That's important. From those two premises, you can infer the consequent. Okay, let me give you an example. If P, then Q, premise 1, premise 2, P, we infer, therefore, Q. Arrow out rule. If P, then Q, we have a conditional statement for our first premise. Our second premise is a formula which exactly matches the antecedent of the conditional statement, right? So we infer the consequent of the conditional statement. And now it has to be precise. The antecedent has to match exactly, and we infer only the conditional. Here's a case where we have two conditionals. Can we apply arrow out rule here? If P, then Q, if P, then R. Can we apply arrow out? The second conditional has P, which is the antecedent of the first conditional, but no. We cannot apply arrow out rule here because the second premise doesn't exactly match the antecedent of the first premise. Okay. I am now going to show you how to construct a proof. I see. Okay, here we go. Okay. Introduction to the method of proofs. So we're going to start with an argument by Winnie the Pooh, everybody's favorite teddy bear. Aha, said Pooh, rum tiddlum-tum. If I know anything about anything, that hole means rabbit, he said. And rabbit means company, he said. And company means food. So here we have Winnie the Pooh. He has an argument. We want to prove that his argument is valid. The first thing we're going to do is restate his argument in more standard logic language form. So, first Pooh says, aha, there's a hole. Right, he sees a hole. That hole means rabbit. If there's a hole, then rabbit. Is here. If rabbit is here, then we have company, right? Hole means rabbit, rabbit means company, and company means food. If we have company, we're going to have food. And you know Pooh, he loves food, so there's an unstated conclusion to Pooh's argument. Can you see what the unstated conclusion is? We're going to have food. Yay. So we've put this argument now into standard form. I've capitalized the words that we're going to use for capital letters. So now we're going to symbolize our argument. Premise 1, there's a hole. Simple statement, so just H. Premise 2, if there's a hole, then rabbit is here. Okay, so conditional, if hole, then rabbit. Second premise, if rabbit is here, then we have company. Third premise, if we have company, we're going to have food. Again, another basic conditional. If company, then food. Therefore, food. Let's see if we can find our symbol here. Yep. Therefore, food. Okay, so we've symbolized our argument. Notice that I've just listed the basic premises here and separated them with commas. That's going to be something standard in the class. Okay, now that we have all of the arguments symbolized, we have our basic premises into formulas and our conclusion into formulas, we're going to construct, step 2, construct the proof table and use it to demonstrate validity. So look at this table. What I want you to notice about this table is that it has 4 columns. An assumption dependence column, that little column, the inference column, and the justification column. For right now, ignore the assumption dependence column. We're not going to think about that column yet, but just it's going to be there later when we introduce different rules that need it. The inference column is where we list our basic premises and then our inferences from basic premises to conclusion. The justification column is where we show which logic rule we used, which valid inference rule we used, and which premises we applied that rule to when we made the inference. Okay, so what we're going to do, we're going to start by listing just our basic premises in the inference column. So number 1, H. This small column here we're going to use to just list the number of rows. So I'm listing the basic premises here, H arrow R. On the justification column for basic premises, I'm just going to say these are basic premises. We're assuming for the sake of determining validity, we're just supposing that they're true. Okay, row 3, third basic premise, row 4, fourth basic premise. Okay, so now I have all of our basic premises listed from our argument, listed here. In the justification column, I've put basic premise. This row just this column, each row just gets a number. Now what we want to do is get our conclusion by applying our inference rules to the basic premises. We only have one inference rule so far. We only know one inference rule, arrow out rule. We know for arrow out rule we need 2 kinds of premises. One premise, that's a conditional, and another premise that exactly matches the antecedent of the conditional. Okay, so here we have 3 premises which are conditionals, and we have one premise which matches the antecedent of one of the conditionals. Okay, so we have this premise here, H, and we see that it exactly matches the antecedent of this conditional on row 2 here. And so we know, since we have 2 premises, one is a conditional, one which exactly matches the antecedent of the conditional, that we can apply arrow out rule to those 2 premises. So I'm going to say here, we have the premise from row 2, and the premise from row 1, and we're going to apply the arrow out rule to those premises. And arrow out rule says when we have a premise that's a conditional and a premise that exactly matches the antecedent of the conditional, we can derive the consequent of the conditional. The consequent of the conditional on row 2 is R. So by applying arrow out rule to the formulas on row 2 and 1, we can derive R on line 5. Okay. R is not the conclusion we're looking for, though, so we're not done. We better add some more rows here. All right. So what are we going to do on row 6? We can now use our new formula that we derived on line 5. And what do we see? Look at line 3. Line 3 has this conditional, if R, then C. We have a conditional statement. Row 5 has a formula that exactly matches the antecedent from the conditional on line 3. So we have the conditions for applying arrow out rule. We have a conditional, and we have a formula that exactly matches the antecedent. So we know that we can apply arrow out rule to the conditional on line 3 and the formula on line 5. So I'm just going to put in my justification column that I used arrow out rule, valid inference rule, arrow out, applied it to the premise on line 3 and the premise on line 5. And if I do that, I can infer what? If I have a conditional and the antecedent of a conditional, I can infer the consequent of that conditional. In this case, the consequent is C, so I infer the consequent. Okay, well, C is not the conclusion we're looking for, so we're not done. We're going to add another row, row 7. Okay. Well, now I have C that I can work with as well. And look at row 4. I have a conditional which has as its antecedent C. At row 6 says C. So I have a conditional and a formula which exactly matches the antecedent of the conditional. So I know that I can apply arrow out rule to row 4 and 6. Put that in my justification column. I'm applying that valid inference rule, arrow out, to the premises on row 4 and row 6. And when I do that, I can infer the consequent of the conditional. Right? Arrow out rule tells me if I have a conditional statement, C arrow F, and I have a formula that exactly matches the antecedent of the conditional, C, I can infer the consequent of the conditional, F. And there we have it. F is the conclusion that we were looking for. So let's have a look at this proof. Let's review quickly what we did. We first started by symbolizing, well, restating in standard form and then symbolizing our argument. Once we had the argument symbolized, we listed the basic premises, each basic premise on its own row. We number the rows. In the justification column, we just say basic premise, basic premise, basic premise. Remember, when we're trying to figure out validity, we're just assuming that these basic premises are true, temporarily supposing they're true to see if they lead to the conclusion. So we just justify them by putting basic premise. Anything that's not a basic premise has to be justified. Any inference, right, this is our inference column, so any inference that we add has to be justified using a valid inference rule. In this case, we only know one valid inference rule. And in the justification column, we put which rule we used, which lines or which rows we applied that rule to infer the formula on the inference column of that row. So this row 5 says, I inferred R by applying arrow out rule to rows 2 and 1. Row 6 says, I inferred C by applying arrow out rule to rows 3 and 5. Row 7 says, I inferred F by applying arrow out rule to rows 4 and 6. And we stopped at row 7 because it is the conclusion we were trying to prove these premises implied. So what we've done now is proven that Pooh's argument is a valid argument. We've done so by showing that through a series of inferences from basic premises to intermediate conclusions to final conclusion, we got there using only valid inference patterns. Okay. So quickly, let's just go over what we learned in this lesson. We learned what a valid inference rule is. A valid inference rule is a pattern of inference which guarantees the logical connection between the premises of the inference and the conclusion of the inference. I told you that we in this class are going to focus on using the basic inference rules, which are inference rules that are self-evidently valid. There's no way of proving them valid. You just have to see that they're valid. We're not going to use derived inference rules or shortcut rules very much in this class, though you will be tempted to do so. We learned the basic inference rule, arrow out rule, and you should be able to see that arrow out rule is self-evidently valid. If you don't see how it's valid, how if the premises are true, the conclusion necessarily has to be true, ask about that. That's important. We learned the method of proof, a method for proving that arguments are valid using valid inference rules, and we do so using a proof table. On the proof table, you should know that the inference column is where you list your basic premises and then each intermediate conclusion or each inference, and the justification column is where you list the rule, the valid inference rule that you used, and what lines of the table you applied that rule to. You're going to have lots of practice doing proofs, but if anything is unclear, make sure that you ask about it first thing.